Hi everyone, I'm Julia, the chemistry tutor. Today I'm going to do a short video on the comprehensive balancing chemical equations. Okay, so I've done a video on types of reactions, I've done a video on balancing equations, and I've done a video on solubility rules, determining your states. So now I'm going to pull all of that together in one tutor session and show you how you are to balance an equation every single time from here on out, okay? Okay, so as you're learning to balance equations, your instructors are giving you the the formulas, and they're probably giving you the products, okay? But eventually you are going to have to go from a word equation without being given the products and do the entire thing. So that's what this video is about, is it is doing the entire thing from a word problem to balance an equation. Okay, so our first one here, we have copper metal. So we have copper, we know is Cu, and we react, it is placed into a silver nitrate solution. So silver nitrate, making sure our formula is correct. He's a +1 and a -1. So that is correct. Okay. So what type of a reaction is that? I have a single thing here and a double thing here. So it's the single replacement reaction. Okay, so copper is going to kick out silver, but we have to check and make sure. Remember, we have to check the activity series with single replacement reactions and make sure that'll happen. So let me pop over to our activity series. Okay, and we're looking at copper and silver. So is copper strong enough to kick out silver? Okay, so our copper is right here, and there's silver, so copper is above silver, so he's definitely strong enough. So we are going to, okay, so copper is strong enough, the reaction is going to happen, so copper is going to kick out silver and hook up with the nitrate and kick silver out all by himself. Okay, so remember, for single replacement reactions, if it's a variable charge metal and copper is variable charge, it can be +1 or +2. Okay, over here by itself, it's 0. Copper metal sitting all by itself has a 0 charge, because if copper metal were charged, you would get electrocuted when you touch it. Okay, so copper metal has no charge, but over here it's in an ionic compound. It could be +1 or +2. Remember, we decide that it's always +2 in a single replacement reaction. Okay, so copper's a +2, nitrate's a -1. So if we swap and drop those, we get 2 nitrates and 1 copper. Okay, so there's our products based upon our type of reaction. Okay, so remember, when we're doing balanced equations, first we have to determine what our products are. That's based on our type of reaction. We have to make sure our formulas are correct. But one too many A's there. Make sure our formulas are correct, and that's based on our nomenclature. And then we balance our atoms on both sides to make sure we have the same number of each atom on both sides of the equation. Okay, so remember, I always start with the one that has the most stuff, and I feel like that's copper nitrate. So I have 1 copper, 1 copper, so that's good. I have 2 nitrates, and I only have 1 nitrate here. So I'm going to put a 2 in front of the silver nitrate to give myself 2 nitrates. And now I have 2 silvers, and I have 1 silver here. So I'm going to put a 2 in front of that silver. Okay, so now I am balanced. I have 1 copper on each side, 2 silvers on each side, 2 nitrates on each side. Okay, so our fourth step in balancing equations if we is we have to say what our states are, and that's based on your solubility rules. Okay. So sometimes you can just look at it and know without looking at your solubility rules. So copper metal, we know copper metal is a solid. We don't need to look at anything to tell that copper metal is a solid. Okay, here it says a silver nitrate solution, which means that is dissolved in water. So we know that that is aqueous because they told us it is a solution. But if we didn't catch that, if we go over here to our solubility rules, okay, and we look up, we've got silver is not rule number 1. So we go to our nitrates, and nitrates are soluble with no exceptions. So silver nitrate is soluble, it's aqueous. Okay, so if we forget by looking at our equation, because it tells us it's a solution, then we know by looking at our solubility rules, that's aqueous. And from those solubility rules, we just saw that all nitrates are soluble no matter what. So we know the copper nitrate is also soluble. And silver metal, sitting all by itself, is a solid. Okay. Your instructors may do a demonstration of that in lab. So you'll have like a test tube with a copper wire coiled inside of it. That's your copper wire. And we'll put a solution of silver nitrate in there. And after it sits for a little while, you're going to get silver flakes all over that copper wire because solid silver is forming. And your solution is going to turn blue because you're getting copper nitrate. And copper nitrate dissolved in solution turns blue. Okay, so we can see by the color change and the solid formation that a reaction is happening. Okay. All right, so now for our next one, we have liquid hexane. And on these, a lot of times for those hydrocarbons, you're not going to know the formulas, okay? The formula is something that you would learn if you were to take organic chemistry, or for allied health majors, if you take Chem 2B, the organic biochem part of allied health chemistry, that's when you would learn those formulas, okay? So when we give you these, we're going to give you the formula, okay? So this says liquid hexane is combusted. Okay, let me erase this over here so I can have some space if I need it. So hexane is C6H14. Okay, and it tells us that it's a liquid. Okay, because this is a covalent compound. That is not on your sheet. That's not on the sheet of solubility. So we have to tell you. So that is a liquid. We know automatically. We can go ahead and put that in. Combustion, we know, requires oxygen, which is a gas. And always, always, always products, carbon dioxide gas. And because it is heated, the water is also a gas. Okay, so remember on combustion reactions, your oxygen, carbon dioxide, water, always a gas, right? You're not going to look that up on solubility rules because solubility rules only tell you solids and aqueous. They don't tell you liquids and gases. Okay, so now to balance this, remember we have the diatomic here. So we're going to do that last. Okay, so we've got 6 carbons on this side. So I'm going to put a 6 in front of my carbon dioxide. I have the 14 hydrogens over here. So if I put a 7 in front of water, I get my 14 hydrogens. So now we have to count oxygens. Okay, so I have 12 here, and I have 7 here. So I have 19 oxygens. So remember, you have the odd number and the even number over here. Okay, and when you have the odd number and the even number, then you double everything except for that diatomic. Okay, so we had 1 of the hexane. So we're going to double that to a 2, double our carbon dioxide to a 12, double our water to a 14. Okay, so you'll see you still have 12 carbons, 12 carbons. 2 times 14, I have 28 hydrogens. 2 times 14, I have 28 hydrogens. So when we double everything, everything stays balanced. That's why we balance those first. Okay? So now we've doubled our oxygens. Now we have 24 here and 14 here, which gave us 38 oxygens. So now we can just put that 19 in front of the O2. Remember, over here we doubled it, and now over here we're dividing it by that 2. So it's always going to be that odd number that you had over there is going to be what you put in front of the oxygen. Okay? So let me get rid of a little of that so we have space on our next one. Okay? And so technically, when you're going to do this, when you're turning it in for a grade, you could leave it like that, or you could erase everything and put the real numbers in, the 2, 19, 12, and 14. Okay? So it might feel really scary, but we just follow the process. Always do the diatomic last. And if you have the odd number on one side and the even number on the other, then double everything except the diatomic and come back and fix that diatomic. Okay? All right, so our next one, we have manganese 3 sulfate. So Mn and SO4. They told us that our manganese is a positive 3. We know sulfate is a negative 2. So remember, if we swap and drop those, the 2 goes to the manganese, the 3 to the sulfate. So 2 to manganese, 3 to sulfate. Okay, is reacted with sodium phosphate. So is reacted with means plus. I have sodium and I have phosphate. Okay, we know, so I'm doing this as we go. Okay, I'm getting my formulas as I write them down. I'm making sure my formulas are correct. So these aren't necessarily 1, 2, 3, 4 in order. Just as you're going, these are the things you need to get done. Okay, so my phosphate we know is a negative 3 and sodium's a positive 1. So swap and drop those. We get 3 sodiums and 1 phosphate. Okay. So looking at that, what type of a reaction is this? I have a double, right? A cation and an anion, and I have a double, a cation and an anion. So they're going to switch partners, right? My manganese with my phosphate, my sodium with my sulfate. So my manganese goes with my phosphate, and my sodium goes with my sulfate. Okay, so now we got to make sure those formulas are correct. So we got our products based on our type of reaction. Got to check all those formulas. Okay, so our manganese, it's a double replacement, so the charge doesn't change. It was a 3, so, excuse me, it's still a 3, and phosphate's a negative 3, so that formula is good. I need 1 of each. Sodium's the positive 1, and sulfate's the negative 2. So if I swap and drop, I need 2 sulfates. Okay. All right, let me make a little space for us there. Okay, so oops, I forgot to mark this. This is our double replacement reaction, and this one here was combustion. And they told us so. Whoop, whoa, I don't know what went on there. Okay, they told us that was combustion. Okay, so now on this one, okay, we're halfway through it. We got our products based on our type of reaction, and we got our formulas correct. So now we're going to balance those atoms, okay? So remember, I start with the one that has the most stuff, and that is most definitely the manganese sulfate here, okay? So I have 2 manganeses here, and yep, 1 manganese there. For a minute, I thought that formula was wrong, but it is correct because it's manganese 3. Okay, so 2 manganese on the reactants, 1 on the product. So I'm going to put a 2 in front of my manganese phosphate, which gives me 2. Okay, I have over here, I have 3 sulfates, and here I have 1. So I'll put a 3 in front of the sodium sulfate, gives me 3. Okay, so remember, I started over here. I'm going to finish over here. Okay, so I have 3 sodiums here, and I have 6 sodiums there. So I'll put a 2 in front of the sodium phosphate to give me 6. That gave me 2 phosphates, and right here I have 2 phosphates. I'm balanced. Okay, so remember, if you start with the one that has the most stuff in it, everything balances itself out along the way. Okay. Okay, so now that we have it balanced, our last step is to look at the states. Okay, so we're going to have to look at solubility rules. First of all, before we even look at the rules, we know group 1 metals are soluble no matter what. That's rule number 1. So we can already mark that as aqueous, and we can mark that one as aqueous. So we don't even need to look those up. Okay, so now we're looking at manganese sulfate and manganese phosphate. Okay, so let's pop over to those solubility rules. Okay, so I'm looking at manganese sulfate and manganese phosphate. So just so we have those in front of us. Okay, so manganese is not rule number 1. So we're going to go to our phosphates. Okay, so salts with carbonate or phosphate, salts with phosphate are insoluble except with rule number 1. Okay, so neither one of those are soluble. Neither one of those are an exception. They are insoluble. They are solids. Okay, so we know that those are both solids. Okay, so balanced, done. All right, so our next one, we have phosphorus acid. So remember the Aus acid comes from the ite ion. So phosphite. Okay, and remember ite is 1 less oxygen than phosphate. And from Phoenix, if you watched my video, we know it has 4 oxygens because 4 consonants. Oh, I lost a letter. P-H-O-E-N-I-X. I'm still spelling that wrong. Okay, anyway, we know phosphate is PO4 with a -3. Okay, so we know phosphite is PO3, -3, because it's 1 less oxygen. And the Aus acid came from ite, so I know it's a -3. I have 3 hydrogens on that acid. Okay, and it is poured over magnesium hydroxide. So magnesium and hydroxide. We know magnesium is +2, hydroxide's -1. So if we swap and drop, we need 2 hydroxides. Okay, so what type of a reaction is that? Okay, we see that we have a double and a double, but remember this is the special case where we have an acid plus a base. So it is a double replacement reaction, but it's the special one that's a neutralization. Okay. Okay, so they're just going to switch partners. My H hooks up with my OH, and my magnesium hooks up with my phosphite. Okay, so my magnesium hooks up with my phosphite, and my H hooks up with my OH. Okay, so to make sure our formulas are correct, right, we're determined our products based on our type of reaction. It's a double replacement neutralization. Remember, in neutralizations, we see the water as HOH because it's easier to balance. Okay, so we've got a +2 and a -3. So swap and drop those. We need 3 magnesiums and 2 phosphates. Phosphite, sorry. And water is water, HOH. That's all good. Okay, so we got our acid and our base made a salt and water. Okay, so to balance this, I'm going to start with magnesium phosphate. It's got the most stuff in it. So I've got 3 magnesiums and 1. So I'm going to put a 3 in front of the magnesium hydroxide. I have 2 phosphites on the products and 1 on the reactant. So I'll put a 2 in front of the phosphorus acid. Okay, since I started over here, I'm finishing over here. I have 1 hydrogen here and 6 hydrogens there. Remember, the hydrogen comes from the acid. So I'm going to put a 6 in front of my water. That gave me 6 hydroxides, and I have 6 hydroxides. Okay, so start with the one that has the most stuff. It all balances itself out along the way. Okay, so we did our products based on our type of reaction. Our formulas are correct. We balanced our atoms. I'll go ahead and put atoms there. Now we're going to do our solubility rules, determine what our states are. Okay, so before we even look at the solubility rules, we know water is a liquid. It was not heated, so it's not a gas, it's a liquid. And we know acids, if you have hydrogens in the front, those are always aqueous. They're always dissolved in water. Okay? So what we're looking for is our magnesium hydroxide and our magnesium phosphite. Okay? So, oh, there's one that is not on this list, so we'll talk about that. That was a good thing I did that. Okay, so I'm looking for magnesium hydroxide and magnesium phosphite. Okay, so magnesium is not rule 1, so hydroxides are here. Bases with hydroxide are insoluble except, and magnesium is not an exception, so that is a solid. Phosphites are not on this list. There are no phosphite. There's a phosphate, but not a phosphite. So the general rule is if it's not on the list, not on list, we consider it insoluble. Okay. So keep in mind, if I had sodium phosphite, that would be soluble because group 1 metal is soluble. Okay, but magnesium phosphite, not on the list, is going to be insoluble. So those are both solids. Okay, so when we go back to here, those are both solids. Okay, and you probably would never know this, but since it's poured over magnesium hydroxide, that kind of indicates it's a solid, but just look it up on your solubility rules. Okay. Okay, so the next one is iron metal. So iron reacts with, so plus, oxygen in the air. Oxygen we know is O2. It's one of our diatomics. Okay, so we already know, if you want to do this now, any metal, except for mercury. Mercury is a liquid, but otherwise metals are solids. And oxygen we know is a gas. Okay, so what type of a reaction is that? Right? We can't switch partners. There's not really partners to switch. There's the only thing you can do with this is to combine them together. So that is a combination reaction. Okay, so our iron hooks up with our oxygen. Okay, so remember I didn't bring that O2 because that's not part of a polyatomic ion. Okay, so on that vein up here, I did not bring the 3 from the hydrogen because it's not part of a polyatomic. But I did bring the 3 from the phosphite because that is part of a polyatomic. Okay, so back to the iron and oxygen. So remember, single replacement reactions. Oh, sorry, this is a combination reaction. So the combination reaction, it's the same rule as the single replacement. If it's a variable charge metal, we assume it's a positive 2. So I have a +2 for iron. We know oxygen is a -2. So that formula is good, one of each. Okay, so I got my product based on my type of reaction. My formulas are correct. Now I'm going to balance those atoms. Okay, and you can probably see there's not really one that has more stuff. I guess the iron oxide. I have one iron on each side, and I have 2 oxygens on reactants, 1 on products. So I'll put a 2 in front of the iron oxide, which gave me 2 irons. So I'll put a 2 in front of him. Okay, so now we need to decide about the iron oxide. Is it soluble or not? Okay, so going back to our electrolytes table, if you'll notice, oxides are not on this list. Okay, and iron is not a group 1 metal, so we are going to assume that it is a solid. Okay, and it actually is a solid. This is one form of rust. When iron nails rust and oxygen in the air, iron nails with oxygen in the air will rust and turn into solid iron. A lot of times that actually makes iron 3 oxide, which is, which is this formula. Okay. But we're going to assume a +2 because you don't know. Okay. So now I have hydrogen peroxide decomposes into its elements. You may or may not have learned hydrogen peroxide. A peroxide peroxide is an O with a -2 charge. So each one of those oxygens is just -1. That is a peroxide is 2 oxygens that are each -1. Okay, so if I have hydrogen peroxide, if my peroxide is a -2, I need 2 hydrogens. Okay, so that is hydrogen peroxide. It decomposes, and this one doesn't really need heat to happen. It really more needs light, which we do this because that's lambda, that's a wavelength kind of thing. Okay, so it just kind of needs light or just to be exposed to the air. Hydrogen peroxide kind of spontaneously decomposes into its elements, right? So its elements are hydrogen, and we know hydrogen is a diatomic, and oxygen, which is also a diatomic. Okay. So balance those atoms. Oh, I'm already balanced. I have 2 hydrogens, 2 oxygens on each side. It's balanced. Okay. So now we are going to do the states. And you guys probably know hydrogen peroxide is a liquid, right? You've used hydrogen peroxide on your cuts. It's a liquid. Hydrogen is a gas and oxygen is a gas. Okay, so done. Oh, by the way, that was a decomposition reaction, right? And they told us that it decomposes, decomposition reaction. Okay. So solid baking soda, if you don't know the chemical formula for baking soda, you need to learn it. Okay, that's the common name. Baking soda is sodium bicarbonate, sodium hydrogen carbonate. Okay. And it says, it tells you it's a solid. So you don't even need to look it up. It's a solid. Okay. I know we said group 1 metals are always aqueous, but this is not in water. We didn't put it in water. It's just solid baking soda. Okay, is heated, so that means it's got heat over the arrow to a high temperature producing sodium carbonate and 2 gases. So sodium carbonate, sodium's +1, carbonate's a -2. And this one might not be fair because you might not know what the gases are. But if you look and see, we've got hydrogens and carbons and oxygens. Our gases are carbon dioxide and water. Okay. So that one might not have been fair, but it did tell you 2 gases, so you know automatically carbon dioxide's a gas, and because we heated it, water is a gas. We know the sodium bicarbonate is a solid. Okay, since these are gases, that sodium carbonate is not in water. right? Everything's solids and gases, nothing to dissolve in, so that means that is going to be a solid as well. Just because we're there, might as well just do the states. Okay, so now to balance this thing, what I want you to recognize is your CO3 is the same there, but it's not the same here. So you can't balance that as CO3, okay? I mean, there is a way if you can visualize there's your third oxygen right there. Okay, that kind of makes it a CO3, and I have two CO3s on that side. But not everybody's going to notice that. Not everybody's going to get that. So I'm going to do it the regular way. Okay. I feel like the sodium bicarbonate over here has got the most stuff in it. It's got everything. Okay. So I've got one sodium on this side and two on this side. So I'm going to put a 2 in front of my sodium bicarbonate. Okay, that gives me 2 hydrogens, and over on the product side I have 2 hydrogens. Okay, that gives me 2 carbons, and over on the product side I have 2 carbons right there, 1 and 2. And this gave me 6 oxygens, and I've got 3, 4, 5, 6 oxygens over there. I'm balanced just by putting the 2 in front of the sodium bicarbonate. Okay, and we already have our states, so we don't need to worry about that. Okay, so you can see that the states just go in when you can put the states in. If you haven't done it after you balance, by the time you balance, put it in when you're done balancing. Okay, so now we have sucrose, and we've been given our formula, is used for energy in our body, utilizing oxygen that we breathe. So I've got C12, H22O11. Utilizing oxygen means that it is going to react with oxygen. And what does that look like to you? Okay, I've got a hydrocarbon and oxygen. That is a combustion reaction. Okay, our body uses enzymes to slow down the combustion to use it for energy. So we're always going to get carbon dioxide and water from a combustion. And remember, oxygen is a gas, carbon dioxide is a gas, and because this is heated, the triangle above the arrow, water is a gas. Okay, sucrose, we're just going to call it a solid. It's actually, if we put it in our body, right, then it dissolves, so I guess we'll call it aqueous. Okay, it doesn't really matter in this case. Okay, so remember we're going to do our diatomic last. Oxygen will be done last. So we've got 12 carbons. So I'm going to put a 12 in front of my carbon dioxide. I have 22 hydrogens. So I'm going to put an 11 in front of my water. Okay, so now let's count our oxygens. I have 24 here and 11 here. So I have 35 oxygens. Okay, so remember we have oxygen here in our compound. So we have to take that into account. We need the 35 to match our 35 over here. We have 11 from our compound. Okay, so the difference in those is 24. I need 24 from the O2. That's an even number. I can just go ahead and put a 12 in front of that oxygen, and that gives me 24. And if we aren't sure if it's balanced, we can do the reactants, products. I have carbons, hydrogens. Oh, I'm almost out of room. And oxygens. Oh, that will not let me write there. Let me move this. So I have reactants, products. I have carbons, hydrogens, and oxygens. On the reactant side, I have 12 carbons, 22 hydrogens, and here I've got 24 oxygens and 11 oxygens. So I have 35 oxygens there. On the product side, I have 12 carbons. I have 11 times 2, 22 hydrogens, and we had already said 35 oxygens. So we're balanced. Okay. So remember I said if you've got the odd number and the even number, you'll have to double. But don't forget to do all of this first to count for the oxygens in your compound before you decide if you have to double that diatomic. Okay, and this was a combustion reaction. I don't think I labeled the one above. The one above was a decomposition reaction. Okay. All right, so now we've got one more left, and then we're going to call it a day. Okay, yeah, we have all of our states in there. Okay, let me get rid of this so I have some space. Okay, so calcium metal. So calcium metal, remember, metals are solids except mercury. Mercury is a liquid metal, but otherwise they're solids, so I can go ahead and put that in there, is dropped into water. So remember from the balancing equations one that when you put a metal plus water, you always get the metal hydroxide and, oh, hydrogen gas. Okay. Since our H's and our OH's split apart, we're going to see water as HOH. So metal dropped into water, we're going to see it as HOH. Okay. So remember, the metal would be a cation if it were charged, and the hydrogen would be a cation. So the metal is going to kick out the hydrogen. Okay, this is a single replacement reaction. So remember, single replacement reaction, we got to go look at those activity series. So we are looking at calcium and hydrogen. So here's hydrogen, and calcium is way up here. So calcium is definitely above hydrogen. Calcium is stronger, so it will kick out the hydrogen and take the OH. Okay, so my calcium kicks out the hydrogen and takes the OH. Oh, okay, and the hydrogen kicks out. Okay, we know hydrogen is a diatomic, so that's why I automatically put the 2 on there to make sure my formula is correct. Calcium's a +2, hydroxide's a -1, so I need 2 hydroxides. Okay, so just as a reminder, on that calcium hydroxide, do not just put a 2 behind your hydrogen, because that means 2 hydrogens. You need 2 hydroxides. Remember to put that in parentheses. Okay, so now to balance this, I feel like the calcium hydroxide has the most stuff in it. Okay, so I have 1 calcium on the products, 1 calcium on the reactants. I have 2 hydroxides on the products, 1 on the reactants. So I'm going to put a 2 in front of my water to give me 2 hydroxides. I started over here. I'm going to finish over here. So I have 2 hydrogens and I have 2 hydrogens. Okay, so I'm balanced. So now let's put the states in there. Water we know is a liquid. That's our pure liquid. Hydrogen we know is a gas. Okay. Let me get rid of that so we can see what we're doing here. Okay, so now we need to look up the calcium hydroxide. Okay, so let's pop over to those. Okay, so we're looking at hydroxides. And hydroxides are insoluble except with calcium is an exception. So it is aqueous. It's an exception to that rule. Okay, so our calcium hydroxide is aqueous. Oh, there we go. Okay, so there we go. That's kind of the comprehensive, taking everything into account to balance equations, determining your 4 steps that you got to do. Determine what your products are based on your type of reaction. Make sure your formulas are correct based on your nomenclature. Balance your atoms on both sides of the equation. Make sure you have the same number of everything on both sides. And then put your states in using your solubility rules. Okay, so that is the general. And then you're going to have to be good at that because we're going to be doing math with all of this. And if you don't have your formula correct, your equation won't balance correctly. If you don't have your equation balanced correctly, then all the math we do with this will be incorrect. Okay? So get your products based on your type of reaction. Make sure your formulas are correct based on your nomenclature. Balance your atoms on both sides and put your states in based on your solubility rules. All right, so that is all I have to say about the comprehensive gathering of balancing equations. Have a great day.